All right, today we are going to be talking about forward bias PN junctions. So let's consider a PN junction that is connected to a voltage source, right? So something like this. So this is the structure of mute. Okay, try this again. Today we're going to be talking about forward bias PN junctions. I am trying to draw such a thing right now. So on the left-hand side, we're going to have our P-type crystal. On the right-hand side, we are going to have our N-type crystal. This is our metallurgical junction. We learned that we should have a depletion region that was slightly larger on the side that is less biased in our last class meeting. So that's what I'm doing here. Just continuing on, I believe we said that our donor side or the N side was more heavily dosed than the P side. So that's why it looks particularly like this. Let's see, we have our bound negative charge over here, bound positive charge over here, and then drawing some randomish number of dopant nuclei on both sides. And putting our charge carriers around. Let's see, so holes over here. Electrons over here. All right, so this is our unbiased PN junction, where, just to be clear, this is our N side of the crystal. This is the P side of the crystal. And under forward biased, we should see that the positive polarity terminal of our voltage source is connected to the P side, and the negative polarity terminal of our voltage source is connected to the N side. And we're going to call this voltage V sub F, right? So forward bias means positive polarity is on the P side, negative polarity of our battery or voltage source is on the N side. Okay, so this might seem like kind of an odd question, but where do we expect the voltage drop in our PN junction to occur? Tosh. Metallurgical junction. So that's X is equal to 0. And it's the same M as I used all throughout our last class meeting. So circling back around to my question, where is this voltage drop VF going to occur in our crystal? In the space charge layer, absolutely right. So it can't occur in our neutral P side because we have a whole bunch of free charge carriers. That's going to be very highly conducting, at least compared to our space charge layer. So we should expect that there's not going to be an appreciable voltage drop over the P side of the crystal, nor will there be an appreciable voltage drop over the neutral N side of the crystal. So all of our voltage drop should occur within the space charge layer, the depletion region, whatever we happen to be calling it at any given point in time. So what does this mean very specifically? Well, we are applying effectively an electric field over the width of the depletion region. How is the direction of this applied electric field going to compare to the internal electric field caused by the? Absolutely right. So our internal electric field is oriented from right to left. Our applied electric field is oriented from left to right. What is our net field going to look like? Exactly right. The difference between these two things. So in our particular case, we are going to see a reduction in our field strength, which is in turn going to lead to a reduction in our barrier potential, right? So the total barrier potential will no longer be V naught, it'll be V naught minus VF. So our built-in voltage minus our forward bias voltage. Since the depletion region width is dependent upon the barrier potential, the depletion region is actually going to shrink under forward bias conditions. So we will see that the width of our depletion region, W, no longer W naught, because we are not at thermal equilibrium, we are applying external stimulation to this system, is going to be the square root of twice epsilon over Q times NA plus ND divided by NA times ND. So everything is the same up to this point, multiplied by V naught minus VF. So the width of our depletion region is going to get smaller under forward bias conditions. So we're going to modify our diagram here in a moment. I want to talk about carrier concentrations now, or actually before we talk about carrier concentrations, let's talk about what that smaller width means. Okay, so we have a reduced barrier potential, and we have a shorter distance to travel if charge carriers were trying to go from, let's say, holes were trying to go from the P side to the N side, or electrons are trying to go from the N side to the P side. So what does that mean? What are the consequences of having a reduced barrier potential and a shorter distance? Diffusion is going to be the probability of diffusion is going to be much greater now, right? And so we should see that effectively show up in our carrier concentrations across the crystal. So I'm going to attempt to draw this thing here. So here's our crystal. this is our new depletion region width. I'm going to make sure that I actually remember to draw that this thing is biased so that we understand what's happening. And let's see here. Holes were in red. So we should have something like this on the P side of the crystal, where this level on the edge is P naught. So our whole concentration on the P side of the crystal is going to start at whatever its thermal equilibrium value is. And as we get closer to the junction, we're going to see a very slight uptick. Okay. We look at our electron concentration on the N side of the crystal, it's going to be something similar. So we're going to see a slight uptick very, very close to the edge of the depletion region, and then it's going to flatten out, and it's going to be N naught, which will be approximately ND over here. And this will be approximately NA over here. So why do we see a slight increase in majority carrier concentrations as we get close to the junction? The negative polarity terminal of our battery is effectively supplying electrons that are going to get attracted to this bound positive charge. The positive polarity terminal is effectively supplying holes that are going to get attracted to this bound negative charge. So this attraction is going to cause this slight uptick here in the region very, very close to the junction, okay, or to the edges of the space charge layer. All right, so now let's look at what happens across our junction, okay? So in our space charge region, our space charge layer, depletion region, whatever the hell we're calling it, we still have effectively very few charge carriers here, free charge carriers. So there is a concentration gradient. Like I said earlier, the reduction in our barrier potential means that we should more easily see diffusion occur. So we might see something like this. I'm going to put a little dashed line right here. So this is Pn naught, approximately Ni squared over Nd on this edge. And then for our electrons, something like this, putting this little dashed line here, where this is Np naught, which should be approximately Ni squared over Na. Okay. So just to be explicitly clear here, we are seeing hole diffusion occur in this direction and electron diffusion occur in this direction. I'm going to label a couple of things here. So this is the electron concentration on the P side of the crystal at what we're going to call X is equal to 0 on the P side of the crystal. James, yes. Yes. So now that our barrier potential and our field strength is lower, we're able to attract charge because they're not getting pushed away by the constant presence of the electric field. Yeah. And this point right here is going to be Pn at 0. So I'm going to define yet another coordinate system for this damn thing. Okay. This direction is going to be x sub n. And this direction is going to be x sub p. So I'm simply saying this is our concentration value at x is equal to 0 in the x sub n direction. This is our concentration value at x sub 0 in or at x sub p is equal to 0 in the xp direction. Okay. So this graph is getting busy, and it's only going to get busier here. This little region of things right here are what we would consider excess electrons, and we have some amount of excess holes as well. Okay. So these excess carrier concentrations, so I'm calling them excess because they are above what our thermal equilibrium levels are there because of a process called minority carrier injection. So effectively, when our barrier potential gets lowered, we are able to inject minority carriers into the N side of the crystal. We're able to inject minority carriers, electrons, into the P side of the crystal. And so we have a lot of extra free charge carriers available for conduction. So what do you think a consequence of having these extra free charge carriers available is going to have? Exactly right. We're going to observe a current now because we have a whole lot more charge carriers that are available to move. Just to be clear here, our holes are moving from left to right, so we're going to see a current flowing in this direction. Our electrons are moving from right to left, so we're going to see a current flowing in this direction. So we're going to have a net current flowing from left to right through the device. And now we're going to do a crap ton of math to describe that. So mathematically, our excess carrier concentrations at the edge of the depletion region are given as follows. So Pn at 0 is going to be Pp at 0 times, or at thermal equilibrium. So sorry, let me restate that because I just made that ludicrously confusing. Okay. Our whole concentration on the N side of the crystal at x sub n is equal to 0 is going to be equal to our whole concentration on the P side of the crystal at thermal equilibrium. So what we see out here on the edge times something, or that something is exp negative Q over kBT times V naught minus Vn. You guys have all had electrical engineering 334 before. What does this exponential here represent? You guys talk about Boltzmann statistics at all? Feel like you had to in order to pass 334. Yeah, this is literally just the probability that an electron is able to diffuse across the junction. That's literally it. That's all that exponential thing means, is the probability that an electron survives the diffusion process. Or a better way to put it would be the probability that an electron is able to overcome this barrier potential. We can write something similar for electrons diffusing to the p side of the crystal. So that's going to be n naught exp negative q over kBt times v naught minus vf. So what we're going to do now is we're going to split this up and put it in terms of only our applied voltage, because the built-in voltage is a constant, so it's not really telling us anything remotely new. Okay. So we can rewrite this expression as p n naught times the exponential of q vf divided by kBt. And this guy could be written as np naught times the exponential of qvf divided by kBt. So hopefully, fairly obviously, the exponential of q over kBt times v naught times pp naught is just pn. So effectively, those were our original probabilities of diffusion occurring due to that barrier potential. And then when we lower the barrier potential, it simplifies to this, where this is only in terms of our applied voltage now. So these are just using our thermal equilibrium values for our minority carrier concentration, right? So this is the majority carrier concentration on the p side times the probability of it crossing this gap is equal to the minority carrier concentration multiplied by the exponential of q times our applied voltage divided by kBt. So Nick. Okay, so fantastic question. So Pn at position 0 is this value right here, right? It is higher than Pn naught. There is more holes here as a function of position than there are holes here. So this is a baseline level that is dependent only on the doping. This value right here depends on the fact that our barrier potential is lowered, and so we are allowing holes to cross our space charge layer. Yep, very good question. So for long junctions, something we have here effectively, the excess carrier concentrations will exponentially decay until settling to their equilibrium values, which is exactly what these exponential functions represent, right? So we'll see that eventually this is going to settle to just Pn naught as we get further and further away from the junction. This guy is going to settle to Np naught as we get further and further away from the junction. Okay? So we can relate this to the diffusion length of our electrons and holes, where I'm going to say that L the diffusion length is the average distance traveled by a charge carrier before recombination occurs. So effectively, the longer our overall crystal is, the more likely it is that our values are going to settle to their thermal equilibrium values as we get away from the junction, get away from the edges of the space charge cycle, right? Because we're allowing it more space to find an oppositely charged free charge carrier and for recombination to occur. So if we had a very, very short junction, we might actually have excess holes before we reach our terminal. For a long junction like this, we see this exponential decay, and it's related to the probability of recombination is related to the diffusion length. And at a certain point, we are effectively expecting all of our excess holes to have recombined with this abundance of electrons on the inside of the crystal. Similar here, as we move further and further away, our probability for recombination gets greater and greater, so that all of our excess electrons have effectively recombined with the majority carrier holes on this side of the crystal. So we can define the change in the minority carrier concentration as a function of position as follows. So Pn at some location x sub n minus Pn naught, our baseline level, is our change. And this is related to our diffusion length as delta Pn at 0 times exp of negative x sub n over L sub n. And we can have almost an identical relationship for the change in our electron concentration as well. So delta n sub p at x sub p is equal to n sub p at x sub p minus n sub p naught is delta n sub p at 0 times the exponential of negative x sub p over L sub p. Using these relationships, I know this is a whole bunch of stuff north. Xn and Xp are the directions into the inside of the crystal from the edge of the space charge layer and into the p side of the crystal from the edge of the space charge layer. Questions are great. There's a shitload of math going on here with new coordinate systems and all of that kind of good stuff. So please feel free to ask. So L is going to be a constant, but it's going to depend on, so it's going to be a constant for the crystal, but it's going to depend on a few things. So it's going to depend on temperature, doping concentrations, and all of that kind of stuff. So have you guys heard of mean free path before? What the hell did you learn in 334? Okay, so mean free path is the average distance traveled by a free charge carrier before it interacts with a lattice site or something like that on a crystal, right? So that's going to determine like how many scattering events that you have and all this kind of stuff. It's a very, very physics heavy related way to think about things like resistance and all that kind of jazz, because you're talking about how long an electron travels before it bumps into something else, changes its trajectory and all that kind of stuff. Diffusion length is a similar thing. It literally means the average distance traveled before this. So what would it be? So it would be L sub P is the average distance into the crystal one of these excess holes travels before it finds an electron to recombine it, right? If we look at our carrier concentration levels here, even at the edge of our space charge layer, right, we have some amount of excess holes. Between here and here is the delta P and delta P sub n as a function of x, right? So this is our distance that we're defining, our excess minority carrier concentration that we're defining. But we can see that this carrier concentration is significantly less than the electron concentration, right? So because there's a lot more electrons than there are holes, even though there are extra holes, recombination is still going to occur, right? These holes will recombine as they travel through this side of the crystal. L sub n and L sub p just represent how long it happens until that occurs. So think about it kind of like our time constant or a rate of decay for a half-life or something like that. It's just telling us how long until a certain amount of these things actually survive. And after enough diffusion lengths, effectively, recombination will be complete and we will get back down to our background thermal equilibrium level. Did that explain things? Okay. So we have concentration gradient, right? We can literally see it. Let me scroll back to this, right? There are more holes here than there are holes here. There are more electrons here than there are over here, which means we are going to have a diffusion current going on. So our diffusion current density, JD for holes, so JD sub P, is going to be negative Q times the diffusion coefficient for holes, D sub P, times the derivative of the hole concentration on the n side of the crystal as a function of x sub n, so its position on the n side of the crystal with respect to x sub n. And because Pn naught was a constant, we're going to see that this is negative Q P sub P, the derivative of delta Pn as a function of xn over the xn, or Q times dP over LP delta Pn at 0 exp negative x sub n L sub P. Making sure I got all of my subscripts there correct. Yeah, so we're talking about hole diffusion, so it should be related to the diffusion length of holes, diffusion coefficient for holes, etc. Yes. No, charge has nothing to do. So this is just 1.602 times 10 to the negative 18. So we need, if we look at this thing dimensionally, right? So this is charge measured in coulombs, multiplied by our diffusion coefficient. So diffusion coefficient is centimeters squared per second, right? So centimeters squared per second. So now we have charge per second. So that's going to be current. And then we have centimeters squared over something in centimeters, right? So that's going to give us centimeters to the positive one in the numerator. And then we have a concentration, which is measured in per centimeters cubed. So unit-wise, this is going to look like amps per centimeter squared. So the Q has nothing to do with the probability. It is literally just giving us the right units so that we get a current. Daniel. So have a negative here, we have a negative here, and then it disappeared over here, right? We're taking the derivative of an exponential function where our exponential decay is negative. So when we pull this negative sign out effectively in our derivative, it's canceling this negative sign, giving us a positive over here. Get terrified when you guys ask me questions about the math, but that one was easy. Thank goodness. We're going to have a similar thing going on for our electron diffusion current density, right? So JDN, and I know immediately what your question is going to be, why doesn't this one have a negative sign? And I'm going to have to stop and think about it for a moment. So let me prepare myself for that. I think actually I can figure that out really easily. I'll talk about it in a second. So this is going to look like Q D N the delta NP of X sub N divided by dxp, which comes out to be negative Q dn ln. Sorry, my stylus, there we go. Wasn't wanting to write. Delta n sub p at 0, exponential of negative x sub p over L sub n. All right, so why doesn't this guy get a negative sign? Because positive current is in the opposite direction of electron flow. So if we had a negative sign here, we could have a not negative sign here because our charge carriers are moving in opposite directions. This one should be X sub P. Thank you. All right. So one of the things that seems a little fishy regarding these relations here, and we're going to rectify that in a moment, is that it seems like the current flowing through the device is dependent on position, because this is a current density that depends on position X sub N, and this is a current density that depends on position X sub P. And we know that in a device, we should see constant amount of current flowing through the device. It should not change as a function of position. So we are going to combine our diffusion current density relationships to look at the total current flowing through the device and see what shakes out, okay? So sorry, I'm looking at this thing here. My notes from, God, probably 2013, and I'm just trying to figure out where my exponential thing went away at. Give me just a second. I'm not sure, so I'll just have to sort this out later. All right, so let me put a line under here. So J diffusion for holes is Q dP over LP times delta Pn at 0. And what I'm trying to sort out is where the hell that exponential function went to. And I honestly cannot remember why I get to throw it away. Other than the fact that perhaps we're just looking at the density at a specific location, right? So if we looked at it at 0, the exponential term would just look like 1. So I'm just going to assume that's what we're doing here because I honestly didn't tell myself what I was doing. So we'll just go with this for now, and I'll try to sort it out before the next class meeting. So Q dP over LP, Pn at 0 minus Pn naught, right? So that's literally just defining what delta Pn at x sub n is equal to 0 is. Is going to be equal to Q times dP over LP Pn naught times the exponential of QVF over KBT minus Pn naught is Q dP over LP. Taking Pn naught out, we get exp of QVF over KBT minus 1. Doing the same thing for electrons, I'm going to skip all of the intermediate steps because it's literally the exact same process. We're going to wind up getting negative Q times dN over Ln and P naught times exp of QVF over KBT minus 1. And when we combine these two diffusion currents, we get our total diffusion current, JD total. That is going to be Q dP over LP Pn naught plus Q dN over Ln and P naught. The negative sign went away here because we know that our diffusion coefficient is going to be our diffusion. Holes are diffusing from left to right, electrons are diffusing from right to left, but the currents are going to be in the same direction, so they could add together. Multiplied by the exponential of, Q VF over KBT minus 1. And we can rewrite this as Q times Ni squared times dP over LP ND plus dN over Ln NA times the exponential of Q VF over KBT, KBT minus 1. So one thing that I want to point out here really quickly, because it might seem counterintuitive, we have a term of VP over LP over here, and then we also have ND. Why do we have ND here? Because the holes are diffusing on the N side of the crystal, because we're dealing with minority carrier diffusion, right? So it seems like we should probably have NA because both of these things are related to holes, but this ND is absolutely correct. We're talking about diffusion on the P side of the crystal where the dopant concentration versus diffusion on the N side of the crystal where the dopant concentration is going to be. Over here, this is related to diffusion on the electron diffusion, which is occurring on the P side of the crystal with the dopant concentration at it. So it seems counterintuitive, but those subscripts on our dopant concentrations are absolutely correct. Okay. We are going to call this big ugly thing right here J sub S, where this is the reverse saturation current density, obviously measured in amps per meter squared or something like that. Okay. And so you can think about this as kind of like, I don't want to call it a background level of current flowing through the device because that's not entirely true. We know that when it's unbiased, we should not have any current. When we talk more about where reverse biasing on what day of the week is it? Wednesday? On Friday, we'll see this again. This is effectively describing the amount of current flowing through the device under reverse bias conditions. So we have this effective constant based on our junction parameters being multiplied by this exponential function, right? So we have VF divided by effectively our thermal voltage, KBT over T, right? 26 millivolts. So for any forward bias voltage that is greater than 26 millivolts, the exponential function bit is going to be greater than 1, right? Because if this were actually exponential, I'm going to have the exponential of 1, either the 1 is still greater than 1. So anyway, so for even very, very small voltages, we start to see the current flowing through this device ramp up exponentially. For a forward bias voltage that is more than, let's say, 5 thermal voltages, the -1 bit does not matter at all. So when we start analyzing diode circuits, we're just going to throw that part away because it doesn't really mean anything for any appreciable amount of forward bias voltage. We'll get to that later. So I wanted to talk about plotting these things, these diffusion current densities. So I'm going to do that really quickly. So if this is our crystal, right? And let's say that this is the edge. So this is negative WP. This is positive W sub N. And this will be J as a function of position. We should see that, let's see, I've been doing electron stuff in blue. So we should see something like this. So this is what J diffusion for electrons is going to look like as a function of position. Poles is going to be pretty much the exact opposite thing. Something like this. And when we add these guys together, literally a constant value across the length of the crystal, which is what our math suggests. All right. So we have described our forward bias current that is going to flow through this device as a function of our applied voltage, as well as the parameters that are related to the junction itself. So our carrier concentrations, as well as our diffusion coefficient and diffusion lengths for those carriers. Another thing that we can look at here is capacitance for a forward bias. Yes. Mhm. Mhm. Let me double check that. There's a distinct possibility that I just made a mistake. I've gotten out of order. This should be L sub P. And this one should be L sub N, which would be consistent with what we have below. Thank you for that, Gabriel. Yeah, my bad. All right. Get back to where I was. Okay, so I'm going to go back to our graph up here and we're going to talk about some things. Okay. So I had suggested that we have a forward bias capacitance that we need to pay attention to. So let's talk a little bit about that and about why that exists. Okay. So we know that for an unbiased junction, we have some amount of stored negative charge over here and some amount of stored positive charge over here. And so we had something that looked like a parallel plate capacitor. We called that our junction capacitor. Okay. The phenomenon that I'm about to talk about is completely separate from that. So over here, we have some excess amount of holes. So we have stored positive charge. Over here, we have some excess amount of electrons. So we have some amount of stored negative charge, and they are separated from each other. But what's really interesting about this is that the amount of stored charge we have is dependent on our forward bias voltage. So we have a voltage dependent capacitance, right? This is what these are used for. Varactor diodes, this is one way to do it. We can also do it with reverse bias, and we'll talk about that in our next class. Okay. So the total charge, let me write this down here. Scroll thingy. Fusion capacitance. The total charge accumulated bless you, due to excess carriers is Q total All right, my laptop is giving me a ton of input lag right now. I do not know why. Q sub n plus Q sub p. And this is going to be equal to Q times our cross-sectional area times Ni squared Ln over Na plus Lp over Nd times the exponential of Q Vf over kBt minus 1. Our diffusion capacitance, C diffusion, is going to be the derivative of this accumulated charge with respect to our applied voltage, which comes out to be Q squared A Ni squared divided by kBt times Ln over Na plus, oh my gosh, it's taking so long for this to show up, Lp over Nd times the exponential of QVF over, is the K going to show up? Nope. kBt minus 1. So this is our diffusion capacitance. The diffusion capacitance is usually going to be significantly larger than the unbiased junction capacitance that we see in an unbiased case. Brody, what up? My intuition says yes. Because if we're taking the derivative, the only where that the voltage actually shows up is right here. So it would be this times this plus, or minus this thing right here, right? None of this has anything to do with voltage. So yeah, that should probably go away. I'll erase it. That being said, just in case this is correct, and I tend to agree with you, for VF, a little bit greater than thermal voltage, it's the same damn thing. So, but I will erase it because I do think you're right. Erase. All right, well, pretend that was erased. I'm going to, that was the last thing, okay, that did it. That was the last thing I wanted to talk about, and apparently I desperately need to restart my computer, so I'm going to do that. So, all right, thank you guys. Reverse bias, PN junctions, next class meeting, probably won't take the whole hour and 15 minutes, so expect to get out probably 30 minutes early. It's not a long thing. Oh no. You get out on Friday. Damn. Yeah. You get to go eat lunch before you listen to Amir talk about other bullshit. All right. Thank you guys. Thank you for bearing with me with this terrifying amount of math.